Page 54. Um, this is page 54. We're talking about, this is a typical way they give directions, right? Continuity, discuss the continuity of each, be sure to state the intervals over which the function is continuous, the values of x which make the function not continuous or discontinuous, and the classification of each point of discontinuity, whether it's a removable or non-removable discontinuity. All right, so let's look at the first example. All right, so how can you tell where a function is not continuous? So in a fraction, the easiest way to tell is, can the fraction have a 0 in the denominator? Well, yeah, this one can, right? If I put a 0 for x, there's a 0 in the denominator. So that is a point of discontinuity at x equals 0 because it's undefined for x equals 0. So at x equals 0, that is a, so I'm answering II, the value of x which makes the function discontinuous. At x equals 0, it is not continuous. Now, so I want to go back and answer the first I, the first I. Okay, we're going to call this 1, 2, and 3. Okay, so example 1, or not 1, I don't know, step 1? All right, it's not steps. What is it? Criteria 1. All right, criteria 1. What is the intervals? Once I have identified where it's not continuous, I can just simply look at the number line and just exclude that. So this is the interval that excludes that value of x equals 0, from negative infinity to 0, from 0 to infinity. So it's not including the point of discontinuity. So that's how I'm going to answer the first criteria, the interval over which the function is continuous. This is the intervals over which the function is continuous. And I've already identified x equals 0 as, for II, for 2, the values of x which makes the function discontinuous. And then part 3, classification of each discontinuity. So I have to now classify x equals 0. What kind of discontinuity is it? Is it removable, non-removable? Can I cancel the x? No. So it's a non-removable discontinuity. All right. Let's go on to B. Okay, so the easiest thing to do is go ahead and factor the denominator. Factor the denominator. Okay. Right. Factor in the denominator, we get x minus 6, x plus 4. So what will make the denominator equal to 0? The denominator is 0 at x equals 6 and negative 4. Right? If I plug in 6, I get 0 in the denominator. If I plug in negative 4, I get 0 in the denominator. All right? So what are the intervals of continuity? So that means I have to write my intervals to exclude these values. So I'm going to start with negative infinity, go up to negative 4, exclude that, union, negative 4. So this is excluding negative 4, up to 6, and 6 to infinity. So I have excluded the values of negative 4 and 6. All right. Now, next, I am going to discuss which one is removable, which one's non-removable. Well, so the x plus 4 I can cancel. That would remove negative 4 as a discontinuity if I got rid of x plus 4. Okay? And that would leave me 1 over x minus 6 if I cancel that out. We're running out of space here. So that means x equals 6 is a non-removable discontinuity. So let's write that out. So how am I going to write this in this space? All right, so x equals 6 is non-removable. And x equals negative 4 is a removable discontinuity. All right, that's it. That's example B. So if I address all 3 parts, part 1, the criteria, criteria 1, the intervals, here it is, that's the intervals. Which values of x make this continuous? X equals negative 6, x equals negative 4. That's criteria 2, the values of x which makes the function discontinuous. X equals 6, x equals negative 4. And it says classify each discontinuity as non-removable or removable. Okay. All right, that's it. Looking at C. All right, so sine is defined for all real numbers. So there's no points of discontinuity. And so it's continuous for all real numbers, right? That's it. That's the interval for its continuous. There are no points this continuity, therefore I don't have to classify anything as removable, non-removable. All right, next one. Definition of continuity. We're going to use a three-part definition of continuity to determine if the function is continuous or not. All right, continuous at x equals c. So here's x equals c. C is 0 in this example. All right, so what we're going to do is, remember the three parts. What are the three parts? The three parts are here from page 53. We're looking at these three parts. Does the limit exist? Does the function exist? Does the limit equal the function? All right, so we're going to plug in 0. Plug in 0. When you plug 0 into this, you got to first decide which part it goes into. 0 is not bigger than 0. 0 is equal to 0, so I'm going to plug it into the top part. So h of 0 equals 0 plus 1, so it's 1. Now take the limit. So I'm going to take the limit as x approaches 1, and this is a piece, I'm sorry, not 1, approaches 0. It's a piecewise function. I'm going to set from the left. From the left will be the top part, okay? And that's going to equal 1. When I plug in 0, I'll get 1. And then take the limit as x approaches 0 from the right. That's this bottom one here. Plug in the 0 and I get 1 again. So that means the limit as x approaches 0, the two-sided limit, since they're the same, the left and the right-hand side limit are the same, it's 1. Now, so now the question is the limit, which is 1, is that equal to the function? Yes. So the answer is yes, it is continuous at x equals 0. Continuous at x equals 0, right? Or c equals 0. I have addressed a three-part definition. I found the limit of the function, right? This is the limit of the function I pointed. And then the value of the function at x equals 0. And they're the same value, therefore it's continuous. B. All right, so let's first find h or f of 2. We're plugging in 2. 2 goes into the bottom one because there's the equal to bar. So I plug in the 2, I get negative 4 plus 8 is 4 plus 2 is 6. Okay, and then let's take the limit. Let's take the left-hand limit first. From the left, that means up here where numbers are smaller than 2. So plug in the 2. 4 minus 8 is negative 4 plus 6. It's equal to 2. And the other hand limit, and we should probably know because we plugged it into the bottom one already. It was 6. So limit as x approaches 2 of f of x does not exist, right? Remember, a two-hand limit, you check the left-hand side, the right-hand side. If they're not the same, the limit does not exist. Now, so it's already violated rule 2, right? This is rule 2. It's violated this one. It does not exist. You don't have to check the third one. If it breaks any of these rules as you check them, if it breaks any of them, or you can jump to the one you suspect that it's going to break, just go to that one. Okay, so it breaks this one, so it's not continuous. So f of x is not continuous at x equals 2. F of x is not continuous at x equals 2 because of this. All right, guaranteeing continuity. All right, so what to guarantee continuity? That means the function has to equal some value, and we want the limits to be the same. So this is the easy part. To make the limits the same, right? We have to have the limit as x approaches, and it's the boundary. It's the boundary that's in question. Okay, ax plus 1. Any kind of number for a is continuous. Okay, so this is a line, this is a parabola. There are no points of discontinuity in the regular line or in the parabola. So the only place it can be not continuous is this boundary. So we're going to take the limit as x approaches 3 from both sides. Okay, so from the right, that's the bottom one. So it shows the other one first. We want it to be ax squared minus 1. And from the left, is, what's that, ax plus 1. Well, we can just plug it in to see what the values are. So that's going to be 9a minus 1, and this is 3a plus 1. Now, for this to work, for this to be continuous, these limits have to be the same. So you just set them equal to each other. So 9a minus 1 equals 3a plus 1. So that's 6a equals 2, a equals 1/3. All right? So we found the value of a, where those two will be the same. Okay? And what happens when I plug in a? So f of x equals, I'm sorry, I don't want f of x. I want f of 3. And f of 3, it's going to fit up the top part. So a is 1/3, so it's 1/3 of 3 plus 1. So that's equal to 2. Okay? And let's see what the limit is. If I plug in 3 into, if I plug in 3 into this expression, right, or if I take the limit, it's going to be, what is the limit as x approaches 3 from the left, and it's 1/3 x plus 1, right? I'm just looking at this part. If I plug in 3 in there, I want to get 1 plus 1, which is 2. What about the other one? Take the limit as x approaches 3 from the right, and a is now 1/3 x squared minus 1. Plug in 3 in there, that's going to be 9. 9 divided by 3 is 3. 3 minus 1 is 2. So yeah, all three are the same. So that worked. Okay. So every time we looked at continuity, it was a two-sided limit. But what if there is no left side of an endpoint? So here is an example of a function that is, the domain is actually from -6 to +6. Okay, the domain is -6 to +6. Then you just need to check to see what's happening as the limit approaches the left endpoint from the right-hand side. Okay, so we want this, we want the limit as x approaches -6 from the right of g of x. That's going to be, just plug in 6, that's 0. And g of -6 is 36 minus -6 squared. That's, oops, sorry, can't see that. So I'm plugging in -6, 36 minus 6 squared, so it's 36 minus 36, so that's 0. All right. Same thing on the other side. Limit as x approaches +6 from the left of g of x equals, if you plug in 6, it's 0. All right, and g of 6 is equal to 0. 36 minus 6 squared, that's 0. Okay, so it's continuous at the endpoints. All right, that's page 54. Let's call it there. That was long enough.